but I want to give about 30 seconds or 60 seconds to make sure everybody who wants to attend can. We had a flurry of activity, last-minute registrations, people coming online. So we're going to pause and just for a second, and we'll be right with you, all right? Suvojit, how are you today?
Good, Jeff. How about you?
I'm doing fabulous. See, this is the pre-show. We should like charge extra and have like a pre-show and an after show. Oh wait, we're not charging anything. This is free.
Well, maybe the main show is free, but we can charge people for the pre-show where we have our fascinating conversations about, like, I don't know, the weather, music. What else do you have on your mind?
Absolutely. You know what? I like the way you're thinking. I'm going to bring that up as a business case. All right. Welcome, everybody. How are you doing? Let's go ahead and start the presentation for today. I want to say right off the bat that, Matteo, if you would go ahead and put the slide deck up on the screen, we'll go ahead and start from there. Perfecto. Everybody, welcome. This is the 6th, I believe, in our Submer webinar series. We talk about everything infrastructure related, from where the hardware is made all the way until how it gets delivered to people and everything in between. That's what we do. It's going to be a great session today, and I want to welcome you to this 6th episode of our webinar. Go ahead and advance to the next slide. I want to introduce myself real quick. My name is Jeff Hardy. I am here to do the content and marketing and messaging and media for Submer. Normally, the smiling face you'd see here would be my brother from Ireland, the amazing Diarmuid Daltoon. His information is below my name. So if you have any questions about Submer products or services or partnerships or things of that nature, Diarmuid is the guy to talk to, and he's a brilliant fellow. So I encourage you to reach out if you can. Also, we have today running the engineering deck, Matteo Mezzanotte in the Submer offices. You actually are fortunate enough. Matteo is in Barcelona, Spain. Our speaker, Suvojit, is in San Francisco. I'm sitting here in the middle of Nebraska. So we are extended out in the cloud. We're all in the cloud together, and that's kind of a fun place to be. I want to say that on the next slide, we talk about how I want you to subscribe to this YouTube channel. Subscribe to all those things. And something else is coming up. Believe it or not, we're starting the Submer podcasts, and we've already got several in the can. So be looking for a way to subscribe. You'll be able to listen to our content, our webinar content, and also additional content that we're planning on your headphones while you're exercising and doing other things as well. So that said, allow me to take a moment and introduce, before I say that, we have I'm gonna back up. We've reserved time at the end for questions and answers, right? And you can feed questions in any which way you want to. If you're watching us on the live stream on YouTube, there should be a comment bar over there on the right-hand side where you can ask questions. We're going to save all those for the end, and we'll be feeding questions to Suvojit after the main body of the webinar is over. And we also have other channels, people feeding us questions back and forth. So there'll be time, we'll be saving time for all that in the end. Don't be shy, jump in and join the conversation. It's always a good thing. That said, let me take a moment and introduce our speaker of the day. Our speaker of the day, his name is Suvojit Ghosh, and he is the Managing Director of the Computer Infrastructure Research Center. That's the acronym CIRC at McMasteruniversity. This facility, it's only one of 3 research and development centers that focuses on data center and infrastructure in the world. It's the home to the Great Canadian Data Center Symposium, which I'm going to ask Suvojit at some point about that because they just had their big annual event. Dr. Ghosh brings a diverse background in research and technology commercialization that spans everything from engineering through life sciences, material sciences, chemistry, and applied physics. And that means he's probably smarter than all of us. He's also experienced and passionate speaker. He has a PhD in engineering mechanics from Virginia Tech, it's a good school, and a BE in mechanical engineering from Javalpur University, and I'm sure I did not pronounce that correctly. But Suvojit, welcome. Is there anything that I missed? I mean, you have a great bio there. Is there anything I missed in that you want to add?
Well, thank you so much, Jeff, for the kind introduction. And thank you for saying my name correctly. That's very rare in this world. But I think you did pretty much everything and projected even more. I'm not as smart as you think. I just know how to make myself look smart. Just a little bit. So, um, uh, I started Circ about 3 years ago now. I take pride in the fact that it's one of very few research facilities in the world on data centers, and we also take pride in the fact that we are partnered with a number of companies in this venture. So yeah, perfect slide for that. So I brag about these things, but we are the only research center in Canada, uh, I guess, that has produced selling products within the first year of operations. We're almost 3 years old. We're a little more than 35 people right now. The way this center is built is a new, I would say, experimental model of industry-university collaboration, where we hold hands with our industry partners all the way from conceptualization to commercialization, which goes all the way from doing customer discovery, customer feedback, uh, some market studies, etc., hand in hand with the research and development, going all the way from if you're speaking in terms of TRL as a metric, it goes all the way from TRL1 out into the mature stage where we help, especially if it's a hardware product, we would help our partners do some small manufacturing rounds, help them figure out supply chain, et cetera, et cetera. If it's software, we go through our network of partners, several different like beta tests, so on and so forth. So that's just me doing my shameless self-promotion.
Shubhavit, if I may, you used an acronym, TRL. Some people know what that means. What is TRL? You talked about taking people from the TRL round forward.
So TRL, or the acronym stands for Technology Readiness Level. I think it came from NASA way back when. It's sort of a universal metric for where a technology is in terms of its realization or manifestation into like real life. So TRL1 stands for, I think, just an idea, like something you're thinking about. TRL2 is you have put some meat into it. TRL3 is you're actively doing research and development, making these numbers on the fly. You have to look up. There's a Wikipedia page, I'm sure, on TRLs if you want to look that up. All the way up to, I think, TRL10 means the product has been commercialized and launched. So it's just a few numbers that are somewhat universally accepted in terms of measuring where a technology is in its progress from someone's head as an idea to being out there in the real world.
Excellent. Why don't we show the slide? You've done quite a few projects, and you have a bunch of partners and sponsors for Circ. Tell us a little bit about those.
So all these partners that you see on the left side of the screen are actively engaged or have been actively engaged with us in developing a product or doing a product development exercise for them. As you can see, it's very, very diverse. Our niche has always been in the computing infrastructure side of a product that they're trying to develop, and it can be either hardware or software. So you can pick any examples. I don't want to pick specific companies out of here, but we have done like a micro data center for edge deployment. We have done a lot of work for telecommunications providers, especially in their NOC design and monitoring systems. We have done work for cable modem manufacturing companies where we have built software for them that looks at the physical plant, especially like a DOCSIS network in real time, so on and so forth. The right side of this slide are sponsors in terms of like people who help us run the Great Canadian Data Center Symposium or are kind enough to make donations to our cause. The Great Canadian Data Center Symposium, GCDCS, we just did the 2019 version of it, which was the second annual GCDCS. It was June 19th and 20th in the same building where we are located in Hamilton, Ontario. It has turned out to, within a year, to be one of the largest data centers conferences in Canada, and has drawn an audience from all over the world this year, mainly because we've gained this reputation where we're focused on innovation as opposed to state of the art. So most data center conferences are geared around what's available right now, what's happening right now, best practices. We try to focus and curate an audience around what's going to happen 5 years from now, 10 years from now. And apparently people like to talk about that. I do.
And that is a perfect segue to our next slide, right?
Yep.
So we're going to talk about the future. You know, so where CERC is focusing, you know, you said from TRL1, right, up forward. So there's things that are just in the idea phase, just in the product development phase, and the conceptualize and science stage. You're seeing all that stuff in real time. So that kind of makes you a good guy to talk to for the future, right?
Yep, and I'm also a good guy to talk to about anything Doctor Who. I've probably watched every single episode out there. Now, CERC is not as good as the TARDIS in terms of the span of time that we can travel, but CERC on the outside is bigger and on the inside is smaller.
Right. Okay, so you know, without further ado, you know, why don't you just launch into it? I want you to take the realm. I'll chime in if I can't help myself. But people are here to hear you speak. So tell us. So first of all, tell us what we should be cautious about.
Absolutely. So this is just what the lawyers make us say. Well, what the rest of this presentation is forward-looking statements. It's me trying to predict the future. Well, me and my colleagues trying to predict the future. So don't take this at face value. Like this is speculation. Some of them is educated speculation, educated guesses. The others are pure speculation. That's basically it.
Wonderful. And because of the parental advisory, at some point at the end, you'll break into some gangster rap, I believe.
Yep, that's the plan. But he might cut us off at that point, as he had already warned us.
All right, so let's go ahead and jump into it.
Cool. So to get into what data centers are going to look like 30 years from now, 20 years from now, 10 years from, basically in the future, we have to look at where the internet is going, and that's where I always like to start. So in this particular graph, if you look at the lower left-hand corner, is kind of where we started like 10, 15, 20 years ago. Applications like email, simple websites, you can tolerate a low bandwidth and a low latency, but as you move towards more modern applications, what you would see is a general trend that the bandwidth requirement and the compute requirement, both two of them kind of go hand in hand, keep going up. At the same time, the latency tolerance keeps going down. So especially if you want to focus right of the 10 millisecond line, like gaming, online gaming, virtual reality, and then autonomous driving or other smart city application, industrial robotics, and very science fiction stuff like robotic surgery. You're looking at very low latency and very high bandwidth. So you have what we're looking like where the internet is going is we need lots and lots of data and compute, and we need it faster. So I guess we're getting greedy, and so if you can go on to the next slide. We're basically getting, we want more and we want it faster. We're getting greedy on both counts. So to translate, if we want more compute and more bandwidth, what we need to do is reduce the cost of compute. So make computing cheaper, make bandwidth cheaper, and at the same time, if we want it faster, we kind of need compute. We need really good networks, yes, but after a particular limit, as I'll talk about towards the latter half of this presentation, we need compute to be located very, very close to the end user. So what we call the edge. If you could go to the next slide, please. So let's first look at the cost, which is one of the main drivers in having more compute and more available to us. We have to somehow make computing cost less than what it does right now. So where does the money go in a data center? Now, this is a Cisco white paper that did a very good survey of this. And what I really like about this is a side-by-side comparison of servers with the facilities. So servers, they assume, have a 3-year life for amortization. On the power and cooling infrastructure, it's OpEx. So you're basically converting CapEx into OpEx and comparing them side by side. What you notice is more than half of the money goes into the actual servers, which is the cost of compute, or IT, as some data center folks like to call it, and the rest, less than half, is on the facility side. So there's always a cultural divide, or like a generally accepted divide between the IT and facility side. What's interesting to note here is about half and half goes towards IT or facilities. Can we go to the next one, please? So, yeah, this one. Thank you. So let's start with the cost of compute. What we have, like traditionally, we have had a lot of commodity servers out there, which have like, single socket motherboards, dual socket motherboards, 4-socket motherboards. Basically, you're increasing the number of CPUs. But about 10 years ago, people started figuring out, hey, we can use GPUs to do compute. At that point, it wasn't exactly the most cost efficient. But this particular study shows that it's a very nice comparison of how GPUs kind of reduce the cost of compute. So this is for, I like this metric a lot. It's dollars per floating point operations per second, which is like a way of measuring compute. And this is comparing, I think, the Intel Xeon CPU with the NVIDIA Tesla from about like the mid 2000s or so. It clearly shows that on the CapEx side of computing, so if you're buying a server, if you add GPUs to your server, the amount of pure number crunching that you can do is about a quarter when you use 1 GPU per CPU to accelerate that computation. And now this note is for double precision calculations. If you go on to single precision, I believe the number is even better. So if we move on to the next one, this kind of there's another really good example which shows just like compute, let's focus on the other 50%, which is the liquid cooling part. So the cooling part. There on the CapEx side, there's a common misconception that liquid cooling is very, very expensive to install. And I get that in some places where you're locked into a particular type of cooling infrastructure and you've been for like a decade, ripping everything out and installing liquid cooling is kind of expensive. But some studies clearly show that, especially if you're doing a greenfield facility, like installing liquid cooling is almost the same cost. Like this is a very ideal scenario, but it's liquid cooling is often cheaper than high density air cooling. And this particular study, and I note again, this is a very ideal study, but it shows it's 34%. Now the links of all of these studies are at the bottom if you want to take a look at that. That being said, so can we move on to the next one? So those were the two main observations that I have about the capital expenditures to make computing cheaper. So from those, I guess I could make the projection that we're probably going to use GPUs a lot more, maybe even more application-specific ICs or other kinds of computing chip design. And we're probably going to use a lot of liquid cooling. Now let's take a little bit of a look on the OpEx side.
Now let me. This is an interesting thing, and I want to linger on that point because I think it's a really important point, right? So based upon the information you've looked at, the studies you've looked at, there's a strong inference that on the pure OpEx side, we know that power consumption is huge, and that's where you're going. But you're inferring on the CapEx side that if you start thinking about liquid cooling of some sort from the beginning, if you start in the front end of it, that the CapEx costs are very close, similar, or within a margin of error. Is that a good way of saying it?
Yeah, I guess realistically it's within the margin of error right now.
Excellent. Okay, good. Please, thanks for the clarification.
Now that's again, the caveat is it's for greenfield construction.
Right.
If you're looking at data centers that exist already, it's kind of expensive, especially if you factor in the cost of downtime associated with like ripping out something that already exists and putting something new. Hey, moving on, let's look at the power consumption. So this is now, if you could go back to the previous one for a second. So if you look at this particular, these are approximate numbers of where the energy goes within a data center. So I'm tracking 100 kilowatts of energy coming into a data center. About a third of that goes to powering a chiller plant. About 5% goes into air handlers. So if you look at it, often 100 kilowatts, about 40 kilowatts or so, almost 40 kilowatts is going into cooling that plays down. The liquid cooling solves a lot of this problem. Now, lights, electrical losses, these are kind of small compared to many of the other things. The other main culprit in this big overhead is the idle IT equipment. So I'm going to touch on that as well. These are the main two areas of saving energy in a data center, which would reduce the cost of compute, would be to reduce the cost of cooling and to reduce idle IT equipment that's sitting in a data center typically. So let's move on to the next one. So let's first start with the cooling side. Jeff, like you were talking about, liquid cooling's somewhat cheaper to install, but the energy benefits that it has is ridiculously better than air cooling. So this is numbers I've cobbled together from, I think, a couple white papers here and there, some analysis on our side. What this shows is, especially if you look at that picture on the top, that's direct on chip liquid cooling. I believe it's a company called RSC. They have they show that under ideal situations in a 10 megawatt data center, but not 10 megawatt IT. It's about, I think, 6 megawatt IT. They have 3.4 megawatts if they switch to direct to chip liquid cooling. When you look at the same data center, but if you're looking at comparison of the various cooling technologies available out there for the same 10 megawatt data center, I think the cost of cooling per year, if you had like the more traditional perimeter crack gallery or craw gallery, you're looking at spending more than $1 million a year, like $1.5 million a year. Whereas if you use even some something close to liquid cooling, like rear door exchanges, passive liquid cooled doors, which is about 2/3 of the way down, you're basically cut this cost by to a third. And if you go all the way to immersion liquid cooling, which is probably, it's somewhat polarizing in the industry today, but by far the cheapest, you're probably looking at spending only about $25,000-$30,000 a year versus $1.4 million. So the cost, especially if you bring it down to the dollars and cents, it's just ridiculously in favor of using liquid cooling. Now,
off the top of my head, that's about 2.2%.
Yeah.
Yeah. Oh, please. I didn't mean to interrupt you. Go ahead.
It's actually less than 2.2%. I think it's because 2% would be about 28,000. But again, this kind of like immersion liquid cooling only works in certain scenarios. So that was my caveat. And that is why immersion liquid cooling is still kind of polarizing. Some people love it, some people hate it, some people want nothing to do with it. But the thing is, we can afford to have that conversation now, but 10 years down the line, when you need lots and lots of compute, I don't think that would be an argument anymore. You either use this kind of liquid cooling, or you're kind of obliterated by competition who has the cost advantage of being less than 2% of what you're spending on your cooling.
But you can imagine that we're rather fond of it.
Yeah.
Please.
So
so you talked about the different types, and you were showing the different types of liquid cooling, and I thought that it would just be a moment. We inserted a couple slides here because some people are familiar with the different types of liquid cooling, some people aren't. So we thought we'd just take a moment, right, and talk about what the different basic technologies there are. And if you look at no, go back again. Thank you, Matteo. The top image there is what's called a cold plate, right? And this is a copper or highly conductive metal plate that you just you bolt on the top of your CPUs and GPUs, and you basically run copper pipe like you would run copper pipe through through a bathroom, right? And attach it to the pipe plate. It circles through and then goes back out, right? It removes the heat that way. And then the next picture down you see is an actual image of an in-rack radiator. This is another type of cooling where you actually basically put an air conditioning unit in the rack itself, right? So the air conditioning unit itself is air cooled, can be either single phase or dual phase cooled in that way. Single phase means that it never changes from gas to liquid and back again. Dual phase means that it releases its heat by converting itself to a gas. And then these units are stacked up inside the conventional racks with alongside the servers. Now we thought it'd be kind of interesting because a lot of people, when we talk about immersion cooling, we talk about what that is, right? And we just took a quick snippet of a video, from one of our tanks, and let's go and show that real quick. And it looks like the window has disappeared. We'll wait for Matteo to bring that back up. But to do it narratively, right? To do it narratively until we get back to that slide. There we go. Let's see if we got it now. There we go. One more. And in immersion cooling, the servers and compute devices are lowered directly into the cooling fluid. It's a dielectric fluid that's non-conductive and non-corrosive, and it doesn't look like the video is going to work. So let's go ahead and describe it. Just go ahead and describe it in the narrative, as they say, right? So.
One of the things I should probably mention here is historically, this comes from my undergraduate training as a mechanical engineer, wherever there is a high heat density requirement, you kind of have to use something like immersion liquid cooling or convection liquid cooling. Think about your car. Your car basically packs about 100 kilowatts into its engine, thereabouts, right? So how do you cool your car? You don't blast air at it. You're basically blasting glycol, basically water glycol mixture through it. And then taking it out to a radiator. You don't need any refrigeration system to cool it. You just pump lots and lots of water or like glycol water mixer to it. So that's a takeaway. So if you look at computers today, where we are right now at the heat density, air cooling is still possible. But whenever the heat density goes up, and it's bound to go up in the future, there is actually historical cases of where it was really, really high, especially if you look at the IBM vector CPUs from back in the day. Liquid cooling was the only option available. Now, there are two things that can drive this. One is you kind of have to use liquid cooling. The other is liquid cooling makes it ridiculously cheaper than anything else. So Both of these are kind of necessary in the future because we'd need lots and lots of compute, and we would want that lots and lots of compute to be cheaper just to be cost competitive, right? So I think where you're trying to go is uh, this is either immersion or direct-to-chip liquid cooling is kind of the way to go. Now, direct-to-chip liquid cooling has a small disadvantage in that, like, you have to basically have a fluid circuitry in there where you have a cold plate mated to the CPU, the memory card, etc. But the rest of the server is not actively cooled by it. So there are a couple products out there, especially the Asetek. They have this thing called ISAC, or in-server air conditioning, which is basically It's a hybrid system. It's a cold plate mated to the CPU with like fins on it that basically circulate air through the rest of the server and cool it there through that circulation. Or you could just dip all your servers into a dielectric fluid, like you're talking about, which is like, so people sometimes, like mechanical engineers like me, we love it because we know that's the most efficient way to cool something. But it's kind of polarizing when you take into account people who have traditionally looked at facilities being absolutely dry and impeccable. Now you're introducing a liquid that drips and can create a mess, so you need a mop to clean things up, et cetera, et cetera.
Yeah, it requires a change in thinking.
Yeah. But so what's interesting, and I'm sorry, I'm digressing a little bit from here, but what's interesting is right now data centers are built in a way where they undergo continuous maintenance and upkeep. So if you're handling servers that go into a data center and they're in a liquid, it makes it difficult. But in the future, 10, 15 years down the line, we'd probably have data centers which are what we call lights out data centers. So they are basically manufactured at a factory, plugged in, and they run on their own for the rest of eternity. And that's when it's not as appalling anymore. Because think about like electrical transformers out there right now. They're actually all sitting in mineral oil, which keeps them cold. This is the same thing.
Right. Yeah, the technology, the idea behind the technology has actually been used since the 1880s.
Yeah, probably even before.
Excellent.
Like, yeah, when you're hot, back in the day, you'd probably go take a dip in the river or a lake or something, right? That's immersion liquid cooling.
It is. You mentioned that the lights out data center, and we've had several of our previous webinar speakers have mentioned similar concepts, and that kind of aligns with our long-term vision for data centers too. Is that more and more, especially data centers at the edge in remote locations and harsh environments, we see it needing to rely more and more upon automation and to be able to run on its own.
Yeah, I'll actually touch upon that just a little bit later in the presentation. So let's get back into the slides that I have. Earlier I was talking about CPU versus GPU in terms of CapEx. Now let's look at the 20% of that pie chart, energy pie chart, cost pie chart, which was energy. Turns out GPUs are actually also way better than CPUs in terms of flops per watt. So they can crunch a lot more numbers per each watt of energy that they consume. And this is a comparison of I think the NVIDIA Tesla K20 versus the Intel Xeon something. So it's an IEEE paper. If the reference is down below, if someone's interested in looking this up. It kind of shows for double precision, GPU is about 3 times as efficient as a CPU from 2012. And GPUs are getting better and better. CPUs have kind of caught up, so it's not like that the ratio has gotten much better since then. It's still about like 3:1 kind of a ratio. But what this kind of projects is that we used to live in a realm where any sort of computing or number crunching was done by a CPU. But what we have seen is in the interest of saving money and doing things faster or doing more things, we actually prefer designing a custom designed chip. GPU was the most generic example of that, but then came around the Bitcoins and the ASICs, or the application-specific ICs that came with the Bitcoins, which were so much better than the CPUs at mining Bitcoin that it's not even cost efficient by far to mine Bitcoins on a CPU-based machine. Similar thing, Google just came out with, and I have a slide on that later in this presentation, but Google came up with the TPU, or Tensor Processing Unit, which is like a application-specific IC for doing TensorFlow type of workload. So machine learning, which is basically just multiplying tons and tons of matrices together. So they designed an IC, they designed a chip that is specifically designed for doing exactly that, and that makes it cheaper, not just in terms of cost of the chips. Now, cost of the chips when you're doing a low production run in a custom chip is probably low, probably quite high, but it must have made the business case because of how much of AI kind of workload they're doing right now. So moving on to the next one. This was a slide right next door. So the picture on the left corner is basically the Google TPUs. So this came out, I think, middle of last year is when they came out with this particular release. And what they show is clearly, for this kind of density, I believe they have about 50 kW per rack over there. I don't think they have published that number, but if you look at the power that's going into it, that would be my guess. And they decided to use liquid cooling. You can see the pipes go like taking a hot coolant in and taking cold coolant out, in a technology that's very similar to what you see in that motherboard over there. This is a 4 sockets with two coolant tubes coming in. And this is the direct-to-chip liquid cooling over here right now. So if you look at now, sorry, that's can you?
I think you want to go back a slide again real quick. Is that what you'd like?
Yeah. Can you hold on?
Go back a slide.
Yeah. Sorry, I'm in a hotel room and housekeeping just kept knocking and knocking.
You understand? You're actually in San Francisco for DCD, correct?
Yeah. Well, DCD and for the meetings. So where I was going here is this particular graph on the right shows why do we need to go to these densities. So sorry, where I was going is, if you look at the picture on the left, it's very high densely packed servers all together. They could have easily spread this out and cooled them via air, but they chose to instead pack them as densely as they could and use liquid cooling. The one on the right kind of shows why. Like the graph, because when you pack things closer, and not just because of the cost of real estate, for many other factors, it's cheaper to pack things closer together. It could be the cost of like copper or other kinds of interconnect between the various servers. It could be purely the cost of management, because it's easier to handle things that are densely packed together as opposed to spread out over like an entire facility. Like, think about it, if the Google TPUs are 50 kW per rack, and if you're going at 5 kW per rack, then each one of what's in one rack would be 10 racks. So what you see here, that's like about 10 racks would basically be 100 racks. And now you're looking at an entire building, entire floor in a building that you need people to manage, you need to clean. There's like a big overhead with that. So
right.
That's another.
And just as a quick aside, and it's a little self-serving, but at Submer we kind of grasped onto this because immersion cooling actually allows you to achieve greater densities because you don't have to leave space for all the plumbing and stuff too. Is that correct?
Yep. Very much so. But the only caveat with that is immersion cooling. Sometimes, most manifestations of immersion cooling is kind of in a tub. where the servers are it's a horizontal rack as opposed to a vertical rack, right? So it's a little
Right.
bit more spread out. You're not doing the most efficient use of floor space possible. Now, there is an exception to these that I've saw, and I saw in the industry, which I'm probably talking about one of your competitors here, but there's a company called, I believe, Isotope. It's a British company, I believe. They have a sealed server with the coolant inside. Now, their limitation is, again, because they're a sealed server with the coolant inside, you kind of have to buy the server from them.
Mm-hmm.
Which puts a damper on what you can use their technology for. But it's the exact same thing, except it's now you can vertically stack them.
Right, right, and what you said is correct. Except I'll just give the caveat that on this end, from with the increased densities, being able to take with immersion cooling, you're allowed you can use conventional hardware, but it also allows you to put CPUs and GPUs closer together. With no fans, no wasted space allowing for airflow. It allows all the processors to be closer together. So in a conventional, we call them, our SmartPods, in the pod footprint, you can take and actually put higher densities, even though you're not stacking vertically, you can get more density per square foot. And then if you add a second level mezzanine in the space, you don't lose your vertical space. So that.
Yeah. Yeah, that's absolutely true. Like especially the second level mezzanine.
Yeah,
I've never seen that yet, but
it's really. We've got some renderings. I'm making a note. I should have sent you one of these drawings beforehand. I'll send you one of the schematics. It's pretty cool.
Yeah. No, that's actually a neat idea. Cool. Okay, now let's come into the topic of how some of the other more experimental things. So far, I've been talking about what's kind of the state of the art. Now, this is a research that we've been active on. This particular paper that's referenced at the bottom, it's from my colleagues at CERT. Here we use purely software tools. We call EAWA, stands for Energy Aware Workload Allocation or Workload Assignment. What we're doing is using some amount of learning from the past to figure out what kind of hardware or what physical server in say a group of servers in a data center or in a network of data centers can handle a particular type of job the best. And with that knowledge, if you do now more intelligent workload distribution, which is easy to do when you're using a hypervisor for some kind of load balancing or containerization where you can move the containers on the fly. That's very easy to do. So using this kind of scheduling algorithm, a workload assignment algorithm that helps you just by shifting jobs around, helps you save about a third of the energy that goes into computing, which is pretty neat. It's just software, just some logic that by shifting workloads can save you a lot of energy. So this is, again, something we'll probably see in the future to make computing cheaper and therefore having more, being able to afford more compute. So I think that kind of takes us to the next one, using similarly the same kind of learning or AI as people like to call it. I still find AI to be a bit of a buzzword, catch-all kind of a place. But this is another piece of research that we've been working on. It's system, the cooling control logic, like control logic for cooling system, where instead of relying on traditional PID control, what we decided to do was use adaptive predictive control. Which is really cool when you think about edge type deployment. So we built this for a cooling unit that would slide into a single rack deployment. Now, what happens in a single rack is it has a very low thermal inertia. So when you go from an idle condition to a full load condition very quickly in, say, an edge deployment, with traditional cooling PID control, the temperature shoots up by a few degrees, and then the cooling ramps up because it senses the increase in temperature and cools it back down. Now, the graph on the right upper corner, it's a study from the Los Alamos National Laboratory, I believe, LAANL. What they show is, and this is again contrary to popular belief, it's not running servers hotter that kill servers, it's actually temperature fluctuations. So the probability of a server failing at between 20 to 30 degrees versus 30 to 41 degrees is roughly the same. Whereas if there is a higher coefficient of variation, that's what COV stands for, goes up from about 2% to about 5%, the probability of failure of servers almost doubles. So think about an edge deployment where you have a stack of servers sitting in a single rack somewhere in a neighborhood out there, say on a rooftop, base of a cell tower. This is stacked with, say, 50 kW of servers that are doing AI kind of workload. Modern servers with Energy Star typically are very proportional, which means at idle conditions, they probably consume like 50 to 100 watts. And at full load, each server can ramp up to like a 1 kilowatt or 1.2 kilowatt. That basically means from being almost no heating, it suddenly turns into like like a gas burner. To keep this thing cool, or basically to prevent temperature fluctuations in something that can change so rapidly, traditional PID control is not good enough. So this is a paper that's coming out. We haven't published this one yet. We filed a patent on this. It's basically through adaptive predictive control, which is basically control based on learning from the past about the environment, and control also based on various other input factors, such as so this algorithm can talk to the PDUs and other power systems. This control unit can talk to the hypervisor, or talk to whatever is doing load balancing, containerization, etc. And it can basically preemptively start cooling before something gets warmer. Again, something that is kind of futuristic right now, but it's a research project that we're working on, hopefully going to turn into a product soon.
Shubhavit, we want to save a few minutes for questions and answers. That's fascinating. But basically, you're saying that just like you get more potholes in the street when the temperature changes a lot, and you get fewer potholes when the temperature doesn't change much at all, it's the same thing as servers.
Yep. Okay, so I'm going to start moving a little faster because I see we're running out of time here. So let's talk about edge compute, and people talk about edge. This is, again, part of the future. Why do we need edge? I've been talking about why we need specific types of edge cooling a lot, and this is just like a funny graphic that shows we kind of, we're getting greedy. We want things faster. We want things right now. So if you run out of toilet paper, you kind of need it right now. So if we move on to the next one, now, why do we need edge? If you look at the graph at the lower right corner, you see many of the applications to the right of the 1 millisecond line are kind of emerging applications. They're real. We know we need them. But you can't really do that. Say you have your end user in New York City and you have a data center in Los Angeles. You can't do that just because of how fast the speed of light is, like how fast light travels. Assuming your latency associated with computing and networking is 0, light would still take about 2.6 milliseconds to bounce from New York City to Los Angeles and back. And so what do we do now? We kind of have to have compute everywhere. We have to have compute on device. We have to have compute basically in every street corner, maybe in everybody's houses. And this, people sometimes talk about, hey, there's enough compute in the cloud. Why do we need the edge? This is kind of why. So if we move on to the next one, to make this edge work, what we're going to see is, what we have right now is the core model. We have a relatively smaller number of very large data centers, which basically house all the compute. But in the future, what we're looking towards is many, many, many tiny data centers spread all out. So to have a mission critical data center right now, you kind of need like facilities guys to be there doing regular checks and balances, audits, maintenance, etc., to keep it up and running. When you have like tens of thousands, hundreds of thousands, millions of data centers within your network, you can't really afford to do that. And that's where the lights out data center concept comes in. We kind of need to have something that is entirely software controlled, where like you don't need a facilities guy to be there. The facilities guy is basically a piece of software, and everything associated with it is automated. So what you do is you take tons and tons of data out of a micro data center that's serving your edge, run this through algorithms that basically figure out what's going on with the data center and take control decisions, et cetera, et cetera. Again, a research project we're kind of working on right now in this area. So let's move on. And to make that work, what we have been looking at is using AI, or basically using specifically data clustering algorithms to do fault prediction. So from a single data center, you can probably look at 100 different variables in real time and figure out if there is something wrong with it before there is an actual fault or outage. So that you don't need your facilities people to do regular maintenance or regular inspections or audits. Your software kind of tells you when there is something funny, and that kind of triggers an action from your maintenance crew. So to do that, we look at variables that people probably don't even think about, like vibration sensors are somewhat traditional. Like we look at temperature, pressure, humidity. We look at network pipes. We look at electrical outputs, but we also do very high frequency sampling of the power lines, like the AC power lines going in. We look at noise information. Basically, we have microphones within the micro data center, et cetera, et cetera. Now, again, this is a research project. We've been working on it for about a year now. We'll see where we land in another year.
Excellent.
Okay, so now I'm going to sum up, Jeff, and then we can start the question. So what would the data center of 2030 be like? It's probably going to be small. Like, there's still going to be the warehouse scale cloud data centers, don't get me wrong. That's where the bulk of our compute would be. But what would be new would be the small 1 or 2 rack systems that form the edge. There'll be a lot of heterogeneity in computing and storage equipment that's optimized. So you'll have ASICs for Bitcoin, you'll have like TPUs for AI workload, you'll have quantum computing for quantum annealing from et cetera, and you'll have the standard general purpose CPUs. We'll have a lot more fault tolerance systems for power and cooling, so that manual maintenance and upkeep becomes a thing of the past. And the usual stuff, software defined everything. So key highlight is using the software defined environment, you can take out a lot of the redundancies, etc. And but it will probably be very, very high density. 100 kilowatt is just a speculation. I don't know what the actual number would be. So on and so forth. But the last bullet point kind of hits it all. What we would need to do is, from a single pane of glass, be able to manage what I call a constellation of data centers. So think about your enterprise application probably now requires you to be at the edge, and you have like 100,000 data centers all over the world. You can't possibly manage that unless you have like a single control panel that has under the covers has all sorts of algorithms automating different kinds of functions, and gives you only the important information on like a single screen. So you're not like not a lot of people can basically fly a 747. You kind of need to dumb it down to a point where there's like 2 buttons to press.
Excellent. Thank you very much, Suvojit. That was a great presentation. I appreciate it. I've got a couple of questions. We're running low on time, so I'm going to grab it real quick. The first question is is related to who's doing it well now. Is there a country or region that you see taking the lead that's going towards your vision of the future data center?
That's an excellent question, and there's no way I can answer this question without making some people mad. But
well, we won't tell anybody this. We're just live streaming to a group of your closest friends.
Yeah. Here's the thing. I see a lot more openness and advancement happening in Europe than in North America right now, especially in adoption of liquid cooling, purely adoption of economization, the government-funded research projects that look at energy efficiencies and bring out actually usable software that you can use to design stuff, et cetera, et cetera. So not a country specifically, but Europe in general is doing a lot more than the rest of the world.
Perfect. The next question is, you talked about the advancements of GPUs and CPUs. We're leaning towards GPUs. Do you anticipate that GPUs are going to get even faster, or are we reaching truly a functional limit?
That's an excellent question. I think it would probably get a little faster with time. But what would be the most remarkable advancement would be chips that are more application specific, like the Google TPU as an example. That's a chip designed to do machine learning workload. You'd probably see the very, very application specific CPUs coming out. Now, I have a speculation. AMD came out with the concept of the chiplets, which is basically instead of having big chip, you have a modular system where you put smaller chiplets to make up your main chip. Now, I don't know if they have it yet, but they would probably come up with, in the future, more and more application-specific chiplets that go onto the module. Intel's gonna come back to the table soon. They were lucky enough to get the creator of all of this recently join them. So it will be interesting to see what comes out of Intel in the next year or so.
And we are running out of time. So Suvojit, first of all, thank you so much for your time. Let me see here what we have here. Our next events, as you know, we're going to be, the Submer team is going to be at the DCD, and I hope you have a chance, Suvojit, to hook up with our team on the ground there in San Francisco. There's lots of other things that we have going on there. These are the OCP Regional Summit in Amsterdam's coming up. These are some of the other things, and definitely Supercomputing 2019 in Denver. That's going to be an amazing event, and Submer's coming big. Are you going to be at Supercomputing 2019?
Yep, I intend to.
Wonderful. It's going to be great. I'm going to try to get there myself if I can. Hope to see you there. That's it. I think that we're going to go ahead and wrap it up now. Is there anything else we need to cover here? I think that's the end. Make sure you subscribe. Go subscribe to this YouTube channel. Go to our website. Subscribe to our social media feeds. We'll keep you informed of all the latest stuff. Subscribe to our blog. Make sure you monitor the RSS feed. We're always posting articles, and our new podcast is coming up, so keep your eyes peeled for that. Suvojit, I can't thank you enough. It's been great having you here. I thank you for your time. You're traveling in a hotel, and it's been great having you.
Well, thank you so much, Jeff, and thank you everybody for listening and tuning in.
Wonderful. Look forward to seeing you all next time. Thanks. Bye for now.